Alright, so this is our actually last topic, and the rest will be reviews and all that, and final quizzes, exams, whatever you call them. And so this is on quadratic forms. And this is actually an application to 7.2 orthogonal diagonalization. But I have to first give you a little bit of introduction to what quadratic forms are. And well, I should perhaps say first what a linear form is. A linear form, so that's of course not what we're going to study now, is something of the form a1 x1 plus a2 x2 plus dot 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 plus an xn. In other words, a linear polynomial in variables x1. But you notice that there is no constant term here. Okay, so this is sometimes called homogeneous form. Form means a homogeneous polynomial of degree 1 in the variables. So x1 and xn are variables here, a1 and an are just scalars, numbers, real numbers. So that's a linear form. So now you can kind of guess what a quadratic form is, the same thing, but now instead of degree 1, we're going to have the degree 2, and only degree 2. So quadratic form, so I'll give you first in two variables will be something like ax squared plus bxy plus cy squared. That's in two variables, so let's see how it looks in three variables. Let me give myself a little more space. Ax squared plus bxy plus cy squared plus dxy, no, that we had that xz, I meant. Xz plus eyz plus fz square. You might have seen this, particularly when you studied perhaps conic sections or in geometry or ellipses and circles, and so that's where this material comes from. In fact, in the book, in the 7.3 in the textbook, they will actually discuss this, but I'm not going to do that. So we're not going to do the whole thing from 7.3. So that's the first thing. So notice some names here we call terms where you have a mixture of variables. So this one's here, and also we have here three here. We call these cross terms, meaning you're crossing two different variables, and the other ones are perfect squares, right? X squared, y squared. And it's somehow the cross terms that kind of are annoying to work with, and the whole purpose of this thing is to get rid of them. Now, I have to explain this a little bit how we will do this. Now, the first thing is, okay, what is this anything to do with linear algebra? It's not quadratic algebra. So, particularly what we have, one of the main tools that we have looked at is matrices. So what has this to do with matrices? Well, the thing is you can represent quadratic forms by a matrix, and even better by a symmetric matrix. Remember, these are the ones that we studied in 7.2, the previous lecture. Okay, so how? Okay, so let me do this first on an example. So suppose we have the example 3x squared plus 4xy plus 5y squared. Okay, so what I want to do is, first of all, I have my, we normally write columns, right? X, Y. So we have this column. Now here we want to put a matrix, but if I work this out, what I'm going to get? I'm going to get expressions, linear forms, two of them, right? We're going to have the first one, this is a 2 by 2 matrix, right? So that's not what I want. I want a quadratic form. And so what I'm going to do is now, and this is I'm going to multiply it also with this, sorry, I shouldn't put any comma here, with a row of the also considered of the variables. Okay? Okay, so before I work out this example on the left, let's look at an example what happens if I do this. And as I said, the matrix is always going to be symmetric matrix. So let me take a symmetric matrix here. I'm going to take the matrix 1, say 3 has to be symmetric minus 2, and then x, y. Okay, let's work this out. I mean, what should it be? Let's look at the dimension of things. This is a 1 by 2 matrix. This is, as I said, a 2 by 2 matrix, and this is a 2 by 1 matrix. So altogether, what is going to be a 1 times 1, so a number, right? Okay, well, a number, it's an expression. And you'll see it's exactly the expression that you get is a quadratic form. Okay, so let's work it out. So we have x, y. Let's do these two guys first. Okay, so that would be 3x. No, so x plus 3y, that's the first one, and the second one will be 3x minus 2y, right? So this is what we normally do to get from a linear system of equations, to get the coefficient matrix and vice versa. But now what happens with I'm multiplying with this matrix, with this row matrix. Okay, so that means I have to multiply the first two elements, that's this, plus the second two elements. Okay, let's expand this, that is x squared plus 3xy plus 3xy minus 2y squared. And you see this is a quadratic form. Perhaps I should put it adding like terms, so we get actually 6xy minus 2y squared. Okay, so let's look a little bit where these numbers go. This number 1, where did it go? Well, it was this number 1, and it eventually ended up here, so it became the coefficient here. Okay, so what happened to the other diagonal element, this negative 2? If you look at what happened to it, it's where it appears is here, right? And then it appears here, so eventually it ends up here to be the coefficient of y squared. Now what about the 3 here? Let's look what happens to the 3. Well, there are two 3's. Well, one goes there and one goes there. It's symmetric, so right? It's symmetric, so there has to be the same elements here. Where do they go? Well, one goes here and one goes there. But notice that they both become coefficients of the same cross terms, of cross products, right? So we get here twice 3. And so that's how we're gonna have to unravel. So this is how we, given a symmetric matrix, get a quadratic form. Now let's look at the opposite. Okay, so now I have this quadratic form here, and how I'm going to make this into a matrix. So what is the matrix that I'm going to associate to it, the symmetric matrix? Well, the diagonal elements were clear, right? These diagonal elements were the coefficients of the powers of the squares of the ideal, the squares of the variables. So we have a 3 here for x squared. Well, we keep the order, right, x, y, and then a 5. So this 3, but let's use the same color that I had here, right? So I had a red color, that becomes this one. The purple guy was the other diagonal element that goes there. Now the green guys, where they go. Now I noted, I said these two green guys add up to 6y. And there's two twice the same, so it's the 6 is half of these numbers. So I have to take this number and half it. So I get 2 and 2 here. Okay, double check that this is what we want. X, y, 3, 2, 2, 5, x, y, that's x, y, 3x plus 2y, 2x plus 5y, so that is x times 3x plus 2y plus y times 2x plus 5y, that is 3x squared plus 4x plus 2xy plus 2xy, I was going too fast, plus 5y squared, and this to combine exactly to give me, wait, what happened? Oh, sorry, it's not the one, I'm pointing to the wrong one, to this one. Okay, so it's exactly the one that I started with. Okay, so the only thing that we have to remember is that we have to take half of the cross term here. Now, this is for 2 by 2. Most of it we're going to do by 2 by 2, but I'm going to do a 3 by 3 case as well. So let's look at an example of a 3 by 3. So we get x squared, say, plus 6xy plus 4y squared plus 12, sorry, plus 12xz minus 2 times yz plus z cube, z squared, sorry, z squared. I have to make, how many terms are there? Well, if that's kind of, you can kind of try to figure this out. This is actually a binomial coefficient, but I'm not going to say that. That calculates how many terms you are. But we're going to only do 2 by 2, so the 2 variables, so we have 3 terms here, and if we have 3 variables, we're going to have 6 terms. Okay. So what is the matrix that we're going to have to build? Well, the principle is going to be the same, right? Our diagonal elements correspond, so we're going to have x, y, and z here. You can actually visualize this, right? So here, what is an element here? Well, it's an x one, an x squared element, so we get 1 here. And y square, that would be the element indexed by this here, right? And then element here, this is z, right? Here would be the element that corresponds to z squared, that's also a 1. Okay, so now let's look at xy. Here is xy, but you also have an yx, that's also xy, right? Because xy and lyx are the same. So we remember what we have to do, we have to divide this number by 2, so we have to put 3 here. Okay, I'll do it in a different color for the next one. Here, xz, this element, this xz comes from this term, but we have to divide it, we have to put a 6 here and a 6 there. Altogether it has to be 12, but we want to evenly divide it because we want a symmetric matrix. And then finally, try to figure it out before yourself, where does this go? Well, it is the yz is either this or this element, right? zy, yz, so they go -1, -1. So that's the symmetric matrix that we get. And so if we then make this this column matrix yz, then I can write this. So this is now I'm writing this as a single vector. I'm using same letter x here. I hope that's okay. So this is my matrix A. The quadratic form this now looks like. Now remember here, what I put here is actually the transpose of this one, right? So I'm going to use that notation, transpose AX. So that's how a quadratic form looks like. So x is a bunch of variables. So sometimes we might write x1, x2, x3. Sometimes we write x, y, z. Depends a little bit on what we want to do. Okay, so that's the first thing. So that's what a quadratic form is. But now, the application. So A is a symmetric matrix, always. And so what we want to do now is to look at the diagonalization of such a matrix. So what is that in general would do? Remember that orthogonal diagonalization, since A is, so we are in this very general situation here that I just described, right? So this is a symmetric matrix, and this is a tuple of x bar is a vector of variables. It could be 2, 3 variables. It could even be more variables. Okay, I'm going to say a little bit more general, but I only work with 2 and 3. Okay, so orthogonal diagonalization tells me I can find an orthogonal matrix P, that was that invertible matrix P, right? And a diagonal matrix D, such that P inverse A, P is D, but then we know that P inverse is P transpose, that is what this orthogonal means. So I can actually write it as P transpose A, P is D. Okay. Now, why do I want to do this? Before I'm going to do this, I'm going to explain why I want to do this. Well, let's look at the diagonal. So an example of a diagonal matrix. We should take a diagonal matrix. I'm going to take a 4. I said I'm going to most of the examples are 2 by 2 and 3 by 3, but I'm not going to do any calculations, so I can make it a little bit bigger here. So let's take a 4 by 4. Let's say 1, 0, 3, 3. That would be a diagonal matrix, right? So 0, 0, everywhere else. Zeros, that's getting very ugly, but okay. Alright, so this is my diagonal matrix T. What is it? It's a symmetric matrix. Diagonal matrices are symmetric, so there corresponds a quadratic form here. So the quadratic form, every symmetric matrix determines a quadratic form, and vice versa. Every quadratic form gives a symmetric matrix, and we have seen that how we can calculate one from the other. So here we have a symmetric matrix. So what is the form? Okay, so let's figure that out. Well, what we need to do is we take the column. Now we have 4 variables. That's the x bar here, right? And then we put D, which is 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 3, 0, 0, 0, 0, 3. And then what we have here is the transpose of this guy, right? So I'm going to just write it as this. Now, let's work this out very quickly. Well, so we get, let me do it here, x1, x2, x3, x4. So what we get here, we're going to get a column vector, right? So what is C? 1 times x1 plus 0 plus 0, 0, so x1. 0, 0, 0, so 0. 0, 0, 0, 3 times x3. And then 0, 0, 3 times x4. Okay, so what has happened is actually these diagonal elements multiply each of these variables. 1, 0 times, 3 times, and 3 times. Now I have to work this out, but what happens? x1 goes with x1, so that gives me x1 squared. x2 times 0, well, that's 0, so I'm not going to write it. Well, let me write it. 0 times x squared. X2 squared, sorry. Now, what is the next one? x3 times 3 times x3, so plus 3 times x3 squared, plus x4, 3 times x4 squared. So notice that, first of all, there are no cross terms, so no cross terms, no mixed terms. And secondly, the coefficients of the diagonal of the powers here of the variables, the square of the variables, that's a 1, a 0, a 3, and a 3 is exactly this 1, 0, 3, and 3. Okay? So a diagonal matrix gives you exactly what we said is annoying is this cross term, gets rid of the cross terms. Okay? So, alright, so good. So it makes sense to go to a diagonal matrix, to have a diagonal matrix. Now, what can we do? We know that if we start with an arbitrary form, quadratic form, it will correspond to an arbitrary symmetric matrix, and then we can orthogonally diagonalize the symmetric matrix. And what does that now do? Well, okay, so I'm going to explain this very quickly. It's not so important because we're not going to use it as an application, but just to see why are we doing this. So we have, let me get rid of this part here so that I can go use, I don't have to scroll back too much. Okay, so so P is an orthogonal matrix, right? Now we have said that that matrices in general always can be thought of as giving a transformation. So suppose this is an n by n matrix, then we know that we can this matrix P gives a transformation that we call T of P, transformation given by the matrix P. And what does it do? Well, simply it takes a vector and you multiply with P, and it gives you another vector. Okay. So let's do this with the vector x. So x was so let's call y the vector p of x, the image of x under this transformation. Okay, and let's see what happens now. Let's calculate this fellow here. What is the quadratic form? Sorry, what I'm trying to say here. Yeah. Is this, sorry, let me see that I want to follow the way the book does it, because you can do it one way or the opposite way, and they want to do it x is py. Okay, sorry. Yeah, sorry. Let me do it the other way around so that it fits the way the book does. Sorry, I just want to make sure. No, I'm going to keep it the way I had. It's a bit slightly different than the book does, but I think it's going to make it otherwise harder for you guys to see what I'm doing here. So I want to calculate now. So okay, x. Remember, x in original was x1, x2 up to xn, right? Was a vector or a column vector of variables, and now y is a new one, so let's call that y1 up to yn. And so we're thinking of x and y as different variables, system of variables, and this we call that a transformation that transforms, or a change of variables, where the variables x are transformed into variables y. Why do I do that? Well, okay, so let's look at so let's look at the quadratic form given by the diagonal matrix T. Let's look at that first. So what is that would be? That would be by definition this guy, right? I remind you of the formula. Okay. Okay. Now D itself, so let's write this out, is D is this fellow, so I'm going to replace D by transpose P A P X. Okay, so this is, I replaced D here by this expression. Okay, I get this. Now I'm going to do a little manipulation. We know that the product of transforms is the same as the transform of the product in the opposite order. This is something that you have to get used to. So it is Px transpose A Px. And now remember, but on the other hand, I can group we are here. This line here, there is a product of 5 different matrices, right? And we cannot shuffle them around. The order is important, but we can group them whichever way we want. This is called associativity. So I'm going to group these two also together. Now this is what I called y, right? So let me use the color here. This was y. So let's replace this by y. So y, t, a, y. Oh, but this is the quadratic form associated to the symmetric matrix A. Well, in variables y. In the variables y. But okay, variables are variables, right? We can name them whatever we want. And this was here, the original one was in the variables. We had this one is in the variables x. So what it says is this. And this is all I'm going to say, and then we're going to do the calculations. It says that if you start with this symmetric matrix A, then it has a certain quadratic form that corresponds to it. Now, if you do a change of variables, so if you change your variables in this way, you get a new quadratic form, but given by a diagonal matrix, which means that it has no longer any cross terms. Remember? Oh yeah, I erased that, right? But so this was the advantage of a diagonal matrix. Now, okay, let's see this all at work. I'm going to start with a 2 by 2. I'll do a 3 by 3, although that's something we not really covered that much, but still, I think it's worth to see at least one example. Sorry, let me get the example here. Yes, okay. So here's the example. So the quadratic form I want to work with is 5x squared minus 4xy plus 8y squared. Yes, okay. So this is the quadratic form. So here's the problem, and this is the kind of problems you're going to get on the homework and on the quizzes. So this is the quadratic form. We have a quadratic form here. And so now what we want is find a change of variables, find a matrix P, which gives a change of variables in the sense that I said here, okay? What we're going to call, just terminology, a quadratic form that has no cross terms, we say it has been diagonalized because of what we're doing here. So find a matrix P that diagonalizes this quadratic form. Meaning this means no cross terms. Okay, so how does it go? Step 1. Step 1 is find the symmetric matrix A. Because now we need a symmetric matrix. And how we do this, we discussed this. The coefficients that you get here will become in the matrix with the one proviso that the mixed terms or the cross terms have to appear twice, right? They have to on the opposite sides of the diagonal to get the symmetric matrix. So we have to take half of them. So the 5 comes here, the 8 comes there, and then the negative 4 is divided by 2 and gets distributed this way, so that we get really a symmetric matrix. Okay. So now, from now on, what we're going to do is for a long time is just orthogonal diagonalization. So, okay, first thing, characteristic equation. So we have to do 5 minus lambda minus 2 minus 2, 8 minus lambda. That is 5 minus lambda times 8 minus lambda minus 4. That is 40 minus 5 lambda minus 8 lambda plus lambda squared minus 4. So that is lambda squared minus 13 lambda plus 36. Yes, okay. So I need two numbers that add up to 13 and multiply to 36. And that would be 4 and 9, right? So that would be lambda minus 4 times lambda minus 9. Yeah, you have to go a bit to the various divisors of 36, okay? So 36 can be 1 times 36, 2 times 18, 3 times 12, and so on, until you find the good combination, if there is one. But I normally have so on. And if you don't find it that way, use the quadratic formula. Okay. All right, so we have lambda is 4, so this is equal to 0, so lambda is 4 and lambda is 9. Okay, so the step 3, the eigenspaces, or the basis rather, orthonormal basis of the eigenspaces. Eigenspace for lambda is 4, so we're going to direct 4 of the diagonal, gets 1, negative 2, negative 2, 4. We go very quickly do this. Row 2 plus 2 times row 1. That gives me 1, negative 2, 0, 0, as we need. So we have our pivot variable x1 and our free variable x2. So this is x1, x2. x1 is x2 is it equal, and x2 is 2 times x2. x1 is 2 times x2, so x2 is 2, 1. And so now we normalize this. It's a bit always ugly, this normalization, because it normally involves, well, let me write down what it is. Involves often square roots, right? So square root of 4 squared plus 2 squared plus 1 squared, that is square root of 5. So the basis will be this vector divided by square root of 5. So 2 radical 5, 1 radical 5. Remember, we divide by the norm. Okay, that's for 4 for lambda equals 9. So what we do is we subtract now 9 from the diagonal, so we get negative 4, negative 2, negative 2, negative 1. Okay? You kind of see always what happens, right? So sometimes you're going to have to introduce fractions. So here I'm going to introduce this fraction here, but it's not going to be too bad. I get, 1. And then if I divide by 4, then I get a half here. And then this is minus 2, minus 1. So I do row 2 plus 2 times row 1. And that is exactly what I want, right? Because now this bottom row has to be 0. If that's not the case, then don't start just plugging 0 because it should be 0. No, double check, because that's how you see that you're making mistakes. Remember, in one of the previous videos, I was constantly making mistakes. I don't know, I was tired. But that's how I keep recovering from these mistakes. Okay, so quickly, this is our pivot variable, this is our free variable, so x1, x2 is itself, and x1 is minus a half x2, so x2 is minus a half 1. I don't like to work with fractions, so let's take as basis, so x2 equals to 2, I'm taking minus 1, 2. By the way, I could actually take x2 equal to negative 2. I don't know if you want to do that, you can do that. And then you see, you can sometimes get, oh yes, I should say that. If you do that, I said the unit vector that you get, the normalization is always the same, up to a sign. It could be one direction or the other direction, because again, you have that freedom. Okay, nonetheless, so what's the normalization in this case? I don't want to do this now, so I'm just going to normalize. I have to take the norm of minus 1, 2, which is again the square root of 1 plus 4, square root of 5. So my basis is this time minus 1 over radical 5, 2 over radical 5. Okay, so this gets me step 3. We are done somehow in the orthogonalization part. We know what P is and we know what D is. Well, let's start with D. We did first 4 and then 9, so we get 4, 0, 0, 9. And then what is P? Well, P is the two basis vectors. Where are they? 2 over radical 5. 1 over radical 5, and this is minus 1 over radical 5, and 2 radical 5. And this is an orthogonal matrix. I repeat, one of the reasons of that this is orthogonal is that these two columns here are orthogonal. If you want to do the dot product of these two vectors, you get 0 because they are eigenvectors of different eigenvalues. That was something that we used. Okay. So that's the story so far. Now, well, we kind of done now, right? Because let's look at what my general explication was. What we need to do is, well, this P gives us the change of variables. Oh, I have my thing on. Let me do another, let's do it in purple. So this gives me the transformation. So now I know that y1, y2 is P x1, x2, okay? So this tells me, in other words, if I want to write this out, which is kind of a bit nuisance, but let me do it. It's 2 radical 5 x1. So remember, I have to put x1, x2 here, right? So that would be minus 1 over radical 5 x 2. And then here we would 1 over radical 5 x1 plus 2 times radical 5 over x2. Which we can also write, it's easier to take the 1 over radical 5 out. We have been doing this often now. So we get 2x1 minus x2 and x1 plus 2x2. So this is the change of variables, which this means what? If I put y1 equal to this expression and y2 equal to this expression, then I have that the quadratic form in these new variables, so the original quadratic form that I had here, where was it? Let me, 5x squared minus 4, let me copy it over here. Sorry, I'm going to copy it here. I hope you trust me, that is correct. This original 5x1, sorry, I switched from xy to x1, x2. I hope that's okay. So 5x1 squared minus 4x1, x2 plus 8x2 square. This is now equal in the purple variables. Oh, which one was pink or purple? I forget now. It was purple. It was pink. Let's do pink. In the purple variables is given by this diagonal matrix, but that's very easy to see. We know that this is 4y1 squared plus 9y2 squared. You don't believe me? Okay, that's y1, y2, 4, 0, 0, 9. y1, y2. Remember, this is what the quadratic form is made. That if you give a symmetric matrix, this is how you get a quadratic form in the whatever variables you want it to be. So this would be y1, y2 times 4 times y1 plus 9 times y2, and work this out and you get exactly that. Okay? So that's it. That's why this P and D give us actually the answer. Okay? So the P is the thing that the question is find the matrix P, that's the P that we now just found, and then also find the diagonalized form of this quadratic form. So a diagonal quadratic form, a quadratic form without cross terms, that is this one. Okay, so this is how this works. I want to do one more example, and then the rest are as homeworks. I told you we normally don't do 3 by 3, but I just want to do one, to show you that this also works. And let me see, I had one here, where did it go? Yeah, it's going to be a little bit more work, but it's worth just looking at. Okay, so this is an example, is the following one. I'm going to use x1, x2 and x3. x1 square minus x3 square minus 4 times x1, x2 plus 4 times x2, x3. This is the quadratic form. So this is a quadratic form. Perhaps a note on in which order do you have to write the terms? Well, there's not really any particular reason you have to write them. In the first two cases that I gave here, I kind of wrote them this way. Some people, and perhaps that's actually wiser, is to first write these three terms the perfect squares, and then the cross terms. So this is the way it's been given to us now, right? First the squares and then the cross terms. But by the way, not all of them are here, right? There should be 6 and only 4. What does it mean? Well, that means that the others are 0. Okay, so step 1, what's the matrix? So we have to get a symmetric matrix that determines this quadratic form. The easiest part is the diagonal elements. I'll make them, that's the 1 here and a -1. And what about the middle one for x2? Well, that's 0, right? So if you want, you can always put the variables here and here, like these are kind of labeled the rows and columns. Then you see this is a 1 here, there's no x2 square, and x3 cubed comes with a -1. Okay, and then once you do this, now let's look at this cross term. Where would it go? Well, x1, x2 is these two positions. Now, I have to take half this number and spread it out, so to speak, right? Evenly divide this number, -4. Okay, what about this guy? That corresponds, let's do this another color. This corresponds to this 4 to x3. No, that's x1, x3. Where is it? It's not there, so it's 0, right? So I should not have used this as blue. Okay, this is not the blue term. So let's make that different term. Let's make that the orange term. Where does this one go? Well, that's this position or that position. Again, evenly distribute 2 and 2. So that's our symmetric matrix. And it has to be symmetric, otherwise we did something wrong. Okay. I hope everybody understands. The main issue is that you have to divide these cross terms, coefficients of these cross terms, by 2. Okay, step 2, we have to find the characteristic equation. That is something we can do, right? We have no problem in doing that. It's a bit more work, we know that for 3 by 3s. So this would be 1 minus lambda minus 2, 0, minus 2 minus lambda 2, 0, 2 minus 1 minus lambda. It's a bit unfortunate that this time we do not have a nice row to expand, and there is even not a good one here that I can use to make a 0. So I'm going to use expansion along a row or column. You can do that. The disadvantage of it is that it doesn't give you a factorization. You have to expand the whole thing and then factor. And whereas the other way sometimes works better. But let's do this. Okay, so this is what I'm going to do. So expand row 1, why not? Okay, so remember, this is, you take this factor, 1 lambda, and then multiply with the cofactor, that are these two guys, but, that is minus lambda 2 minus 1 minus lambda. I made it a little myself small here. So that's these two. And then the other cofactor, I'm going to go over this row, the other factor is -2, but when you do more than 2 rows, we always have to be careful here about the signs, right? So this comes with a negative sign, so it's -2, and then what is left is -2, 2, 0, minus 1, minus lambda. Okay, that's the only thing you have to be careful about. If you get this, sorry, and I should put this with parentheses, right, because I'm multiplying. If you do this wrong, of course, yeah, then you're in trouble. Okay, let's work this out. 1 minus lambda, this is minus lambda times minus 1 minus lambda minus 4, and it is plus 2 times minus 2 minus 1 minus lambda minus 0. Okay, we have to expand all this. Let's take our time and first expand the inside part. That is the minus lambda plus lambda square minus 4. That's not expanding here anymore. And then this is minus 4 times, so this 2 and minus 2 comes minus 4, and then expanding is a plus 4 lambda, minus, yeah. I have to still expand further the first part here, that is a minus lambda plus lambda square minus 4, that is using the 1, and now using the negative lambda, plus lambda square minus lambda cube plus 4 lambda, plus 4 lambda. Okay, and now let's take at all the terms we have. Well, let's bring everything to the other side because I don't like negatives here. So this is, let's see, lambda cube. I bring this other side, so 0 equals lambda cube. Okay, so if you don't know what I mean, is I'm going to do lambda cube to both sides. This is equal to 0, right? So I do plus lambda cube. Lambda square. We have a lambda square, another lambda square, this and this. If they both go to the other side, they become minus 2 lambda square. I hope that's okay. What about the lambdas? We have a 4 lambda, minus lambda. So that is 8 lambda, 7 lambda. But they go to the other side, it becomes minus 7 lambda. And then the 4 and 84 cancel. Okay? If you don't see this how you do work it out yourself and then convince yourself that this is the answer. Don't ask me where does this come from. You have to check it. Just double check that this is what it is. Okay, so now we factor out lambda. We have to factor, right? But there's no constant term. That's a good thing always. So try to factor out the lambda, and then we have lambda squared minus 2 lambda minus 7. Two numbers that multiply to now I'm getting myself a little bit. Did I do a mistake here? Plus 4 lambda. Yeah, no. Minus lambda, plus 4 lambda, plus 4 lambda. Okay, I did something wrong, guys. I'm sorry. I was pontificating so much, but then somehow I made a mistake too. What did I do wrong here? Okay, that's missing. Minus lambda, minus 1 lambda, minus 4. I have my matrix here. 2 minus 1 lambda. And then I expand it there, and I get minus 2, 0, minus 1 lambda, so that sounds correct. Then I had to expand this thing, that is minus lambda plus lambda square minus 4, yeah, this is plus 2 lambda, so plus 4 lambda. Okay, and then I get minus lambda plus lambda square minus 4 plus lambda square minus lambda cube plus 4 lambda. No. Something I did wrong and I don't see where. Because the equation that I have to get is I'm sorry guys. What the reason I'm holding is I know it comes out nice and this is not going to be factorized, factored well. So I did something wrong. I'm looking at it again. Minus 1 minus lambda. Okay, so this and then this matrix. Let's see that I've got everything correct there. Yes, and then this plus what is left is minus 2, 0, minus 1 lambda. Okay, that seems correct. Now, minus 1 lambda. So let's mark this out. That is minus lambda, minus 4, and that is minus 2. Yeah. And now I expand this. Minus. I see this is a plus lambda here. Jesus. Okay, that's a plus lambda. So we get a plus lambda there and minus lambda square here. This is the two guys that change. Now I'm getting there. That's what it had to be. Okay, because what do we get now? So let me do the over from this part over again. Otherwise it gets confusing. I'm sorry for the little hiccup. Okay, so this was expanded this wrong. So we have this. Now let's expand this now. This is lambda plus lambda squared plus minus 4. And now we make negative lambda, so minus lambda squared minus lambda cube plus 4 lambda plus 4 lambda equals 0. So the negative 4 and the 4 cancel. And then what else cancels? And this lambda square cancels with this negative lambda square. So what I'm left is minus lambda cube plus 9 lambda. But I'd like to bring everything to the other side, or get positive sign, so change the signs. Lambda cube minus 9 lambda equals 0. Now this is not hard to factor. First of all, I can factor out a lambda. and then lambda squared minus 9, that's a double product, that's a difference of squares, lambda minus 3 times lambda plus 3. Okay, now we're on track. So we have three roots, lambda equals 0, lambda equals 3, and lambda equals negative 3. Step 2, eigenspaces. So, okay, what is going to happen now is we're going to have three different eigenvalues, so three different eigenvectors, and those are going to be orthogonal already. Okay, that's so we don't have to worry here that the matrix is going to orthogonal matrix after we normalize them. Okay, so let's do that. So step 1, eigenspace for lambda equals 0. So this is the original matrix, which I'll let me get the original matrix back up, otherwise. Yes, there, that's 1, negative 2, 0, negative 2, 0, 2, 0, 2, negative 1. Okay, we have a 1, so it's a bit more work, of course. Row 2 plus 2 times row 1. That's going to go quickly, hopefully. So we're going to have a 1 minus 2, 0. So I'll multiply this with 2, we get a 0 there, and negative 4, and a 2, and here we get 0, 2, negative 1. Okay, we know kind of that, not surprising that we're going to have some fractions here, so we're going to divide by minus 1/4. And we get 1, negative 2, 0, 0, 1, minus a half, 0, 2, negative 1. That's a good thing, because if I now do row 3 minus 2 times row 2, what I'm going to get is 1 minus 2, 1 minus 2, 0, 0, 1, negative a half, and then 0, if I multiply this with 2 and add up, subtract, then I get 0 there, and I get 0 there. Great. So we have already our pivots. These are the pivots, but we need a 0 above the second one. Okay, so we have to do one more. Remember, we have to reduced echelon form, because we are solving in a system of equations, basically, right? So reduced echelon form. So we have to do row 1. Row 1 is row 1 plus 2 times row 2. I'm using row 2 because that's the pivot I'm using, and this gives me. So I multiply this with 2 and add up there, so I get a 1, a 0, and a negative 1, and 0, 1, minus a half, and this is just a 0, which I'm not going to write anymore. So we now know also what our free variable is, so this is going to be the free variable, right? x3 is the free variable, and so we have x1, x2, x3. x3 is itself. What about x1? From this equation we see that x1 is x3. And the other equation says that x2 is equal to half x3. So if I factor this out, I get x3, 1, a half, and 1. Now I don't like this, so I'm going to take x3 equal to 2, and the basis vector that I would want to work with is 2, 1, 2. But I still have to normalize. Same as with the 2 by 2. So we have to normalize, we have to take the norm of this guy, 2, 1, 2 here. That is square root of 4 plus 1 plus 4. Oh, that's square root of 9. 9. Look how nice. It's 3. So we have as the normalized form is so the orthonormal basis for this eigenspace is this vector divided by 3. So 2 thirds, 1 third, 2 thirds. Okay, that's the first one. We have to do 2 more. So now lambda equals 3. That means we're going to subtract 3 from the diagonal. So that means I'm going to plug in 3 in this matrix here, right? So we're going to do lambda equals 3. I'm going to plug in here, so I get minus 2. Okay. Yeah, I'm sorry. I'll write a matrix here. I want you to see that I don't, well, I want you to see where I make mistakes, but you cannot warn me, right? You cannot yell and scream, hey, you're making mistakes, so you have to hope that I find out myself if I do. 0, 2, 0, 2, negative 1. Okay, so this was the original matrix A, so I'm going to subtract 3 from the diagonal and get negative 2, negative 2, 0, negative 2, negative 3, 2, and then 0, 2, and then subtract 3 from the diagonal, so negative 4. Oh, okay, so good. Luckily, I can make a 1 in the first row there by dividing by minus a half. I could do also the second row, the third row. You want to do that? Okay, I'll do it. 3, 3. It's not necessary. No, sometimes I don't do this. I just work with one pivot at a time, but okay. Okay, so this is 1, 1, 0, minus 2, minus 3, 2, and then 0, 1, negative 2. Okay, so the next thing I want to do is row 2 plus 2 times row 1. So that is 1, 1, 0, 0, so I'm multiplying this with 2 and add, so 2 minus 3 is minus 1, and then there's a 2, and then 0, 1, negative 2. And now I see that I can make a 0 row. I'm going to do a little bit sloppy, okay, I hope you, by now, I'm going to do row 2 plus row 3. So I get my 0 in the middle. I'm not supposed to do that, but then you move the 0 row and then you're done, okay? So I get 1, 1, 0, 0, 0, 0, 0, 1, negative 2. But okay, so this is now gone, but this pivot, I need a 0 above of it. Okay, so this middle row is gone, so I have only row 1 and row 2 left. So I'm going to do row 1 minus row 2. This is to get this guy 0, and this is, what does it give me? So I'm multiplying with negative 1 here, and add up to that, so I get 1, 0, 2, 0, 1, negative 2. That's it. So our pivot variables x1, x2, free variable x3. So we have that x1, x2, x3 is equal to x1 from this equation is negative 2x3, and this tells me that x2 is 2 times x3, so we get negative 2, 2, 1. Okay, we have to normalize, don't forget, normalize is always something you need to do, and so we get the norm of minus 2, 2, 1. And this again nice because it's 4 plus 4 plus 1, so that is radical 9, that is 3. So our orthonormal basis, I'm going to just write basis here, is minus 2/3, 2/3, 1/3. Okay, and then finally lambda equals negative 3. So lambda is negative 3. I'm going to do that. I don't know. I'm going to have to copy the matrix again. Okay, I hope that now you're going to double check it, right? That I don't make mistakes. So I'm going to subtract negative 3, means adding 3 to the diagonal. So lambda equals negative 3. The matrix you get is 4, negative 2, 0, negative 2, 3, 0. I'm adding 3 to the diagonal, 0, 2, and 2. Okay, this time I'm gonna have to get some fractions, so I'm gonna do row 1 divided by 1/4 of row 1. I prefer that than row 2, right? I can do row 3 again, so that was not so bad last time to do that, maybe a bit quicker. So we have now 1 minus a half, 0, minus 2, 3, 0, and 0, 1, 1. I have to get rid of this guy, so row 2 is row 2 plus 2 times row 1. So I'm going to multiply this with 2, so I get 1 minus a half, 0, then I get 0 there, times 2, that's minus 1 plus 3, that's 2, and then just 0, well, that's not too bad, we didn't lose anything here, 0, 0, 1. What can I do? Oh, that's not good. No, because I'm not going to get, so, okay. Shit, what did I do wrong? I added 3 to that. Oh, I see, I copy. Okay, the matrix was, okay, here guys. This was the matrix, and you see how silly I am, I keep writing things wrong. That's of course the advantage of working on a paper, because then you can just go back up the paper and look at the same time. So this was the matrix, so I got a 0 there, it should have been a 2 here, so this would have been a 2 here, and that's much more like it, right? So again, let's divide row 2 by 2. I could have done the other thing too. okay, 1 minus a half, 0, 0, 1, 1, 0, 1, 1, and now, of course, get rid of the last row. That gives us the echelon form. It's not reduced, so we're going to have to do one more step. And 0, 0, 0, right? So I'm not writing that, so I'm going to do one more step, is row 1, we have to do plus a half, row 1 is plus a half, row 2, right? Yep, okay. So what we get, so I have to multiply this with a half, I get 1, a half minus a half is 0, and then I get a half there, 0, 1, 1. So the pivots are x1 again, x2, and the free variable is x3. So yeah, so we have x1, x2, x3. x3 is itself, x1 is minus a half, x3, and the other one is minus x3, right? Okay, so that is minus a half, minus 1. 1, I don't like my negative, my negative signs are fine. I don't want this fraction, so I'm going to look at minus 1, minus 2, 2. And now I have to normalize this, so normalize. So I have to take the norm of this guy. And it's 1 plus 4, again 3. Okay, so the basis that I'm going to have is minus 1 over 3, minus 2 over 3, 2 over 3. Okay, so what we've done is we haven't done really orthogonal diagonalization of a 3 by 3 matrix, but I'm claiming I'm done. So step 3, why am I done? Let's what I have to do. Well, I put the 3 that I found in as the columns of my matrix, right? So the last one was here minus 1/3, minus 2/3, 2/3. Then we had, where was the other one? Minus 2/3, 2/3, 1/3, minus 2/3, 2/3, 1/3. And then the first one that we did was 2/3, 1/3, 2/3. 2/3, 1/3, 2/3. Now, I am assured that this is an orthogonal matrix for 2 reasons. First of all, the columns are unit vectors because I made them, I normalized them. And different columns are orthogonal to each other. Or the vectors are orthogonal to each other because they correspond to different eigenvalues. Okay, so that's with 3 by 3 matrices, we have this too. What can go wrong with the 3 by 3 matrices if you have only 2 eigenvalues, then things might not be diagonalizable, but even if it's diagonalizable, you have a basis, 2 basis vectors, but those 2 basis vectors might not be orthogonal. And there is a trick to do that, it's called the Gram-Schmidt procedure, but that's for a later course. Okay? So that's B. Now the corresponding D was given by the corresponding eigenvalues. I think this was the order that I did them, right? A double check. Yes, okay. So this is the diagonal matrix. So this tells me now step of course a little bit numbering here, step 3, but I think this was already, I don't know, step 2. See, there was 2 step 2s here. I knew that was kind of off. So this is step 4, this was step 5 now. What is so if y, y1, y2, y3, this is what I call y bar, that is p times x1, x2, x3, this is what I call x bar, right? If we do this, here is the formula. If I do this change of variables, the pink change of variables, then these new variables, I'm going to get a diagonal form, namely the corresponding diagonal form therefore would be, so let me write it, so if let's call this y, then we would have y transpose dy, and we know what this comes out to be 0 times the first one, so 0 times y1 squared, 3 times y2 squared, minus 3 times y3 squared. Okay, so this is the diagonalized form of the original quadratic form. And again, this is unique. There's only one way to do this. well, no, I shouldn't say that. Sorry, I should say that up to the order of the variables, because I have a choice in which I can write these guys, right? Yeah, sorry, it's not entirely unique, but that's how you solve it, and that's what you need to do. Okay, and that's all for today. I'm gonna now assign some homework problems, and then we do a test and so on it later.